Hello and welcome to today's video. Today we're going to be talking about optimization and in particular finite element analysis and optimization. This is one of two videos. In this first video we're going to be talking about FEA, finite element analysis and optimization, and its impact that it has on the product lifecycle when you're developing a product. We'll have a look at what that means in terms of conceptual designs, and we'll have a look at the differences in terms of cost and time, looking at designs which have been led by CAD, so traditional iterative development, i.e. You come up with a CAD design and you assess it via CAE, computer-aided engineering, or FEA, and when we'll compare that to an FEA-led design. So this idea of using optimization very early on in the product lifecycle to actually define the major load paths, for example, within a structure, so that you come up with a much better structure right first time. So we'll have a look at a conceptual design and we'll compare that to a more traditional approach, and then we'll have a look at, if you're working for a business and you're looking at conceptual studies, if those conceptual studies are successful, you would then go on and, once you've run the business, take those concepts through to production. So we'll have a look at that second scenario, this idea of taking a concept through to production and using optimization techniques within that environment as well. So today's video is really all about FEA and optimization within the product lifecycle and the development cycle of a component. This second video then goes on and talks a little bit more about the theory of optimization, some of the pitfalls that you might come across when you're looking at optimization. We'll have a look at some simple mathematical examples demonstrating the power of optimization, how optimization can come up with a solution, and then we'll have a look at the different types of optimization that you may well come across. Topology optimization, topometry optimization, that sort of thing. Okay, so today's video, one of two videos. Like I say, today is all about optimization in the design cycle. The next video, the second video, is more about the theory of optimization and the different types of optimization that are out there. Okay. Okay, so let's consider finite element analysis and optimization within the design cycle. Now, my expertise, my experience is in the automotive industry. So this presentation draws upon some of my experience in the automotive industry and considers some of the products, some of the scenarios that I've seen whilst working in the automotive industry. So here's an example of the sort of thing that I was historically involved with: development of vehicle vehicle structures to ensure that their crashworthiness was acceptable. So here we've got a highly complicated model with a full vehicle crash test. We've got dummies, we've got airbags, we've got wheels, we've got joints. It's clearly highly non-linear. So that's the environment that some of these examples are based within. So this is what we're going to talk about today. We're going to start by thinking about FEA and optimization in the product lifecycle. We'll have a look at, like I say, we'll have a look at a conceptual example, and then when we do that, we'll have a look at a comparison of costs and timings of a concept which has been led by CAE, computer-aided engineering, or finite element analysis and optimization. So you'll hear me use those terms pretty much interchangeably, FEA and CAE. FEA is finite element analysis, is actually based on the finite element method. So you've got the finite element method, finite element analysis is based on that, and essentially that involves using an awful lot of matrix algebra. So hence we tend to use computers to do finite element analysis, so hence computer-aided engineering. So you may hear me refer to those terms, computer-aided engineering and FEA, almost interchangeably, because generally will we use FEA, or will we use computers, or we use CAE to do some FEA. So we'll have a look at a comparison of a concept which has been developed using CAE versus a more traditional CAD-led approach. We'll then have a think about, okay, well, if that concept is successful, how do we then take that through to production, and how can we potentially integrate optimization and optimization techniques into the production example. And then we'll summarize that. That will summarize today's video. And like I say, the next video then we'll move on and we'll have a look at the theory of FEA pitfalls, sorry, the theory of optimization, pitfalls of optimization. We'll have a look at a simple mathematical example, and then we'll think about the different types of optimization. Okay, so optimization in the product life cycle. So what I've shown here is we can think of this as time along the x-axis, and we've got three different approaches here. We've got a more traditional approach without CAE or without FEA and optimization. At the top here, we've got a design which is being developed with early CAE in the product lifecycle, and then at the bottom here we've got a design which is being developed using CAE before the CAD. So we've got a CAD-led design and a CAE-led design here. Okay, so without any CAD, historically, what would typically happen? You would produce some drawings, some CAD based on experience and judgment, and then you'd produce some prototype tooling, and then you would produce those parts, you'd do some testing, and then almost certainly you'd need to go back to the drawing board, update your CAD, produce some more prototype parts, do some more testing, and then you might need to go through that iteration yet again. So you can see we've got this timeline, and the final design is produced right up here due to the fact we've had to go through these three iterations. That's historically what people would do, and then pretty much at the turn of the century, people started using CAD-led design. So rather than producing parts, producing CAD early on, and then prototype tools and testing it, you could use CAE to influence your design. So CAD would be drawn based on experience and judgment. And then you can produce a CAE model, computer-aided engineering model. Essentially, you're using FEA as a verification tool here. So you've come up with a design, and then you're using CAE to assess that design, and then there will be a feedback loop there. So potentially the first time you do that, it would fail. So you'd go back to the CAD, update your CAD, update your FEA model, your CAE model, reassess the design, and you go round and around in this loop. And eventually you get something which you're happy with, and then you would produce your prototype tooling, produce your prototype parts, and do your testing, and hopefully that will be successful. And you can see by doing that, by moving from this traditional approach to this CAD-led design, with CAE integrated into the design process, the design cycle has been, the time to get to the final design is hopefully reduced. And then what you can use, and that's the process that a lot of suppliers are still using. A lot of automotive suppliers, a lot of general suppliers are still using. A lot of design houses are still using. So we're using experience and judgment to come up with a design, and then using CAE as a verification tool. What an optimization-led design is starting to do or CAE-led design, rather than using experience and judgment to come up with a design and then using CAE to assess that design, it actually flips that on its head, and it says, okay, well, let's use CAE, let's use optimization right at the start to understand what the major load paths are. Let's use that information and feed that into the CAD, so that we come up with a better CAD part. We'll then produce a CAE model, almost certainly there'll be some subtle differences there due to manufacturing processes or whatever. We will produce a CAD part, produce a CAE part, and then assess that. And then again, there's this feedback loop. There might be a need to update the CAD and update the FEA model. So you go through this process, through this feedback loop, and then eventually you get something which you're happy with. You produce your prototype tooling, and then you prototype parts, and then you do your testing. And again, you can see that the amount of time it takes to get to the final product has come down. Okay, so all of these three design approaches, you can see by moving from one to the other, we're seeing a reduction in the amount of time it takes to get to the final component. So I want to show an example of how you would do that. Here's a conceptual study that I was involved with. It's for an automotive supplier. It's what they were calling a rear cross-car beam. So this is for a convertible sports car with a folding hard roof. So this structure is designed to sit behind the seats. It goes from one side of the vehicle, from the B pillars on one side, to the other side of the vehicle, to the B pillars on the other side. And what they wanted, there were certain hard points, certain non-designable regions. So attachments to the body in white, attachments for the roll hoops, attachments for the roof and the seat belts and so on, which were non-negotiable. They couldn't change. They are non-designable regions. They have to be there. However, the component which was joining those, they didn't really care what that looked like because it was non-cosmetic. It wouldn't be seen by the customer. They just wanted it to be structural to join those non-designable parts. So we've got a designable region. Here's my package space. So if we can combine that non-designable region with that designable region, we end up with what is known as a topology package space. So we can use our FEA structure, our optimization tools to come up with a design which is efficient, identifying the major load paths, connecting these non-designable parts together. And here is an example of doing that. So here's an animation showing that topology study that was carried out. Now, whenever you do a topology study, you have variables, objectives, and constraints. So in this case, the variables were the material. Where would we put the material? So this is our space. And so the variables are the elements within that space. Where are we going to place the material? The objective for this particular load case, let's say we were looking at the rollover load case, so we're applying some loads in the hoops. The objective is to minimize strain energy, i.e. we want this structure to be nice and stiff. We don't want it to deform, and we don't want to see any plastic deformation or anything like that. We'll talk about that in a bit. And the constraints, well, rather than using all of this material, clearly we wouldn't use all of that material. We'd end up with a very heavy part if we did that. Our constraint is having, let's say, only using 30% of the material. So our variables are where our material is. Our objective is to minimize strain energy, and our constraint is to only use 30% of the material. So let's consider now actually what's happening in this animation. Let's come out of the presentation. Let's zoom in there. So we would start with this structure here, iteration, our baseline design. We might have all of that space, but in order to meet the objective, we only want to use 30% of the material. So what the software does, it will take the stiffness and the density of the material, take all of those elements and come up with an imaginary material, which is, let's say, 30% of that. Of the real values, and so therefore in theory it's only using 30% of the material. It will assess the structure based on the load case that you've got. It's only using 30% of the material, and it will output strain energy. So iteration number one, using only 30% of the material, we can understand the strain energy within that structure. Okay, so if we were to consider the that scenario, let's plot strain energy. Let's give that so that's got the symbol U against our iteration number. So our baseline design, when we've got 30% of all of the elements, we would assess the structure and we'd get a certain amount of strain energy here. Okay, so what the software then says is, well, if I want to minimize the strain energy, I'll look at all of the elements within the structure, and any that are heavily strained, I need to make those stiffer. So I'm going to add stiffness to those, I'm going to add density to those elements. But if I'm only going to use 30% overall, if I'm adding material in heavily strained regions, I need to remove material from areas which are not heavily strained. So I'm only using 30% overall. And by doing that, the software starts to migrate the material away from the heavily strained areas, away from the areas which are not heavily strained towards the areas which are heavily strained. So by iteration, so this is iteration number 1. So by iteration number 2, my strain energy might have come down. Because what's happened is it's looked at iteration number 1 and said, if I want to reduce the strain energy, I need to remove the material from the areas which are not heavily strained towards the areas which are heavily strained. And if I'm going to do that, I need to and by doing that, I will reduce the strain energy. So what tends to happen then is if you plot your strain energy over your iterations, you start to see this sort of thing. It starts to come down. So the overall strain energy, as you increase the number of iterations, so from iteration 1, 2, 3, 4, 5, 6, 7, 8, and so on, it will look at the amount of strain energy within the model using 30% of the material by migrating the material away from the areas which are not heavily strained towards the areas which are heavily strained, and eventually it will converge on a solution. You'll see that graph is gradient, is negative here. It's quite large, quite negative, and it's approaching 0 here. We're not making much progress actually at the end here. As our iterations increase, we've converged, what's known as convergence. We've converged on a solution. The gradient is approaching 0 there. So we're starting to migrate the material right up until this point here, and then at this point here, we've no longer making much progress. We're not seeing much reduction in terms of the strain energy. So what does that actually look like? Well, that's what this image here, that's what this animation here is showing. It's showing the density of the elements, and it's cycling through all of the iterations. So initially, all of the material is there, and you can see it's all at about 30%. And then as it cycles through the iteration, you can see the densities are increasing. So these red areas, densities approaching 1. So those are identifying where the major load paths are. If we take a screenshot of that final iteration, we would see something like this. So here we can see this is showing us the elements which have got a high density in order to minimize the strain energy, to make this nice and stiff for this particular load case, whilst only using 30% of the material. Then what you would do is you would take that and you would use that to inform your design. So you can then take that design and you can come up with a solution. So here's the solution that we came up with in this example. Here, for example, you can see by where are we? Put that laser pointer on. So you can see here that diagonal brace there. That is, you can see that in the animation here. That diagonal section there. Clearly, that's a major load path because material is being moved in that direction, and we can see that diagonal here. Okay, so what we're looking at here, clearly this is only half of the structure, so only this half of the structure here. Okay, but you can see that diagonal brace there, You can also see this structure here. So we've got this H in the center here, and again you can see that is interpreted into a design there. So rather than coming up with a design based on experience and judgment, we're using final element analysis and optimization tools to understand where the major load paths are, and then we can take that information and we can interpret that into our design. Okay, so that was an idea of a conceptual study carried out using topology optimization, what's known as topology optimization. The second sort of optimization that was then carried out on that structure is something called topometry optimization. So this is a large casting. The supplier that I was working for at the time made large magnesium castings, and the beauty of a casting is clearly you can change the thickness locally on the structure. So that's what this second animation is showing. Again, think of your variables, your objectives and your constraints. Again, this time your variables are the thickness of the structure. So you've got your elements, and this time your variables are for this particular manufacturer, we could manufacture anything between, let's say, 2.3 mil was the minimum wall stock, up to 7 mil. Beyond that, there would be manufacturing issues with porosity and that sort of thing. So our variables our elements could be anywhere in that range, and our objective might be to again minimize strain energy. So we are looking to optimize that structure, and again we would take the final iteration and we would take that and interpret that into a design. So here you can see an interpretation of that design. Most of the structure is at the minimum wall stock, which is what you'd expect. That's a very efficient structure. It's thin, it's large section, but there are certain areas, certain major load paths. For example, this diagonal brace here, you can see that is quite thick. So the software was saying we need to make that structure quite thick there, and you can see that's been interpreted into a thick section there. So clearly that's a major load path. So the initial design, which was come up with using topology optimization, we've then used topometry optimization to assess that design and to inform the thickness of the castings within that design. The third sort of optimization that was then carried out on this was something called shape optimization, and this time the variables are the shape changes, i.e. the thicknesses of the depths of the ribs and the thicknesses of the sections and that sort of thing. So this time, same idea, you input certain information telling the software how those variables could possibly change. So for example, you can see that rib there is being scalloped back. You can see this section here is increasing and decreasing. So we're saying, okay, it can be between these minimum and maximum values. And again, the software was asked to iterate the design to come up with the most efficient solution. So when this design was developed, we used 3 different sorts of optimization: topology optimization, and then topometry optimization, and then shape optimization. And then an assessment needed to be carried out looking at the design to ensure that it met the specifications from the customer. So this particular component, there were 2 main load cases that we were looking at. There was the rollover protection, where we would apply loads into the roll hoops to ensure that this structure wouldn't fail during a crash, to ensure that the material didn't exceed yield. And secondly, the case that you're looking at here now is the roof opening load case, where loads are applied to the attachment points. If I just turn that on there, so the attachment points where the roof is attached to this structure. we wanted to make sure that as that roof opened and closed, the material didn't exceed 70 megapascals, because beyond that fatigue was going to be an issue. So we knew that as long as it was below 70 megapascals, fatigue wouldn't be an issue. That's fine. So during the optimization runs, those two load cases were used to develop this structure. However, there still needed to be a verification run at the end of development. So we took the conceptual CAE design, and from the CAE model, we outputted a final FEA model, which we could then use to assess the final structure. So that's what we're looking at here, this final assessment of the structure. Here we've got the roof opening load case, and you can see most of the structure is quite highly stressed, but none of it actually is above 70 megapascals, which is great. If it's not highly stressed, then that begs the question, why is it there? You know, if it's not doing anything, you might as well remove the material. Let's make it lighter. So this is exactly what we wanted to see. We've got a highly stressed structure. However, it doesn't exceed 70 megapascals. You're not exceeding the fatigue value, which is associated with this material. We then looked at the rollover protection load case, where we're applying loads to the roll hoops. So this is actually a non-linear load case. The optimization was carried out in a linear environment. We've approximated the non-linear load case to a linear load case, but in this assessment here, we've got a non-linear assessment of the structure, and we're applying a load to the roll hoops, and you can see the majority of the material is below our target of 6% strain. Beyond 6% strain, we would likely see failure, so we wanted to ensure that we were below 6% strain. And we can see the maximum plastic strain here is 5.7%, and that's actually in this diagonal here. And you saw earlier the depometry run up-gauged this area, significantly increased the thickness of that, and we can see why now. That is clearly a major load path for the rollover protection load case. So with this design, we've got our concept, and our concept has been developed using optimization techniques. We've produced an FEA model. From the FEA model, you can output an IGES surface. So this isn't a proper CAD part. This is a part which has been generated from the elements. So it's an approximation of the part which the customer could then input into their CAD models for a package check, to show basically what it looks like and to ensure that it's not going to interfere with any or clash with any of their other components. The time to develop this concept, approximately 2 weeks. When we were doing this, I was using an external supplier, and they were looking at a couple of weeks turnaround time to do the sorts of optimization run that we've just been talking about. Time to generate the rough CAD model, so it's going to go from the CAE model to the CAD model, 10 minutes, literally just turn these elements into surfaces, stitch those surfaces together. There's your CAD model. If, however, you wanted to generate a full three-dimensional CAD part, that would be approximately 6 weeks. That would be significantly more complicated. You'd have to worry about draft and ejector bosses, and all these two-dimensional surfaces would have to be proper three-dimensional surfaces. Most of them, you can see they're 2.3 mil thick, where we were talking about earlier, but you've got some areas where you would need to increase the thickness and so on. These are clearly just mid surfaces based on these elements. So now that we understand that, we can start to quantify the savings that we would see using this optimization-led approach compared to a more traditional CAD-led approach. So this is what we were talking about earlier. So we've got our optimization-led design, and we're doing CAE to start with, and then we're doing CAD. If the concept is successful, this conceptual study is successful, we would then produce CAD if the customer was happy with the design at this stage here. If we compare that to a traditional CAD-led design, we might come up with a design to start with, and then do a CAE assessment. So rather than using CAE to drive the design, we're using CAE to assess the design. So we've come up with a design, we've used CAE to assess it. We've then updated the CAD and we've used CAE to assess it. And then we've updated the CAD again and we've used CAE to assess it. Now, this is all based on when I was working for this supplier, 1 year's work, which was approximately 40 concepts. So I said, okay, well, if we were looking at all of those concepts and we are using optimization-led designs, what would be the potential saving in terms of cost and time compared to a traditional CAD-led design? Now, in order to do that, I've had to make some assumptions. The initial CAD, 6 weeks. So like I was saying earlier, this part is quite complicated when you start to need to look at draft and ejector bosses and that sort of thing. We've said potentially that's going to take 6 weeks. The FEA assessment and the optimization structural development, 2 weeks. Like I said in the last slide, that's what the supplier was doing in terms of looking at topology, and then shape. We were looking at a couple of weeks. FEA assessment, so to do the CAE-led design, do all these optimization tools, we've got that down as 2 weeks. But a CAE assessment would still take 1 week. You still need to build your FE model, apply your material properties, your boundary conditions, and your loading and all that sort of thing. So we've still FEA assessment would still take a week. The CAD-led approach requires 3 iterations to get the structural performance working. Okay, so you can see so produce our initial CAD and then CAE assessment, that's 1 iteration. Update the CAD, CAE assessment, 2nd iteration. Update the CAD, CAE assessment, 3rd iteration. Cost assumptions at the time when I was outsourcing this, a CAE analyst was £45 an hour. A CAD analyst was £35 an hour. If we make the assumption of 40 hours a week, we can start to put some costs associated with this. Okay, so with the optimization-led design shown in green here, after 2 weeks when we've done this, these topology runs, these optimization runs, topology, topography, and shape, the concept is complete after 2 weeks at the cost of about £3,500. The CAD is available for the initial package check. We've outputted that CAD that we saw earlier, this CAD here. So we've got a representation of the part which we can give to the customer. The FE model is available to the customer for structural verification. So as you saw on the previous slide there, we've got our FE model. We could give that to the customer, to the OEM, and they can actually assess the design to check that they're happy with it. Now doing that gives them some confidence actually in terms of the quotes. Historically, we would base our quotes based on estimates and previous experience for a particular component, a particular load case requirement. But now, rather than using that estimate, we've now got physical proof of our part being suitable or not for that customer. If and then only if at that point the customer is happy with the design, then do we have the expense and the time necessary to produce the 3D part such that we can have the final 3D CAD available after 8 weeks and the cost of £12,000, and we can give that to the customer. The thing to notice there is most of the deliverables, 3 out of 4, 3/4 of them, are here, right at the front. If we compare that to a CAD-led design, in red here, so computer-aided engineering design, computer-aided design, sorry, we've got 6 weeks to start with, and at that point, so we've come up with a concept which we think is going to work. We can give that concept to the customer. They can, it's available for their initial package check, and that's going to take 6 weeks and cost about £8,500. We then go through this development cycle. So we refine the design, and then the concept is complete after 11 weeks and the cost of £16,500. And at that point, the final 3D CAD model is available to the customer after that time and cost, and the FE model is also available to the customer for final structural verification at that point. The thing to notice there is that most of the deliverables are at the end of the design process. You've now got 3/4 of the deliverables at the end of the design process. Okay, so you can see the optimization-led design is cheaper and quicker, and it's also likely to come up with better designs because we've identified those major load paths. It's possible that we've missed a major load path in this initial design. We've then refined it and we've got it working, but fundamentally it's not going to be very efficient because we've missed the major load path. So it's not going to be as efficient as a CAE-led design where all the major load paths have been identified right at the start. So the CAE approach is likely to be lighter and better performing product. Okay, but the timings and the cost, clearly they're approximate. Okay, and we can see that from all these assumptions that we've had to make in order to understand the times and the cost for an optimization-led design versus a CAD-led design on this slide here. So the previous example showed how we would look at a conceptual design potentially using optimization techniques. That hopefully shows you why that's likely to be more successful in terms of securing the business. What this next slide does then is shows how we can use that concept and take that through to production, and how the initial load paths identified in the early topology study or the early optimization studies should make their way through to the final prototype part, the final production parts. So here we've got a beam, it's a cross-car beam. So this is for a vehicle, sits in front of the occupants behind the dashboard. So this is for a left-hand drive vehicle. You can see your steering column, your steering wheel would attach here. Your HVAC, your heating and ventilation system would attach here. This side you would have glove box and airbags and that sort of thing. So this goes across the width of the vehicle. This attaches to one A-pillar, this attaches to the other A-pillar, this attaches to the tunnel in the middle of the vehicle, and there you can clearly see holes for the ventilation system in this vehicle. So there we've got an early topology study. So what happened here, the customer came to us and said, well, we know the A surface, we know what the the part on the outside needs to look like so that we can attach all our parts to it. But what we don't understand is where the ribbing needs to go in the back of this casting to meet all of our load cases. So we did an early topology study where we filled the back of the casting with solid elements, and we looked at exactly what we were looking at earlier. So our variables were the material, our objective was to minimize strain energy, and our constraint was 30% of the material. So what we're looking at here is a plot of the density of the elements, and you can see the highly dense elements at the end of the run after it has converged on a solution, identify where the major load paths are, and we can see those major load paths make it through to the part here. So you can see this rib here is being driven by that topology study, and then that makes it through to the final CAD part, which has actually made it through to production. We also see, for example, this rib running down here, which is this rib here. That rib there can clearly be seen there. So here we've got an example of a prototype part, a production part, a concept study, and we can see how that makes its way through to the prototype part and ultimately through to production. If we compare that CAE-led design, that optimization-led design, compared to a previous CAD-led design, you can see there's just lots of cross ribs everywhere. So it's nice and stiff, which is great, but because there was a real lack of understanding of where that stiffness is required, that part is too stiff and therefore too heavy. It's stiff in all directions, but it's, there's no need for that. There's just lots of ribs added to make it nice and stiff, but therefore it's over-engineered, it's too heavy. So if we can compare a CAE-led design to a CAD-led design, the CAE-led design, we can see hopefully is going to be much more efficient because there's only ribs where they are necessary. So let's summarize what we've seen today. Okay, so the CAE-led designs in these examples has achieved the following. The conceptual designs reduced cost and timing by approximately 80% when solid CAD is not required. So for an initial conceptual study, when the final CAD part is not required, the customer hasn't decided to go ahead with that conceptual study. The supplier has saved themselves approximately 80% by looking at using optimization techniques. If, however, the customer does decide they want 3D CAD, there's still a saving of 30%. The part is still much more efficient. The design is likely to be better. It's likely to be lighter, cheaper, quicker, more robust, more efficient. So therefore, you're more likely to win the business, particularly because the customer's confidence in business development quotes have improved. So previously, if you were looking at a CAD-led design, the customer might say to you, I want the part to do this. And then you as a customer, as a supplier would say, well, it's going to cost you whatever, 50 euros, it's going to weigh 10 kilos. And based on all of that, based on our material cost, based on our manufacturing processes, we can give you, we can work out what it's going to cost you. But the customer ultimately has got no confidence in your quote because it's simply based on your experience. There's no proof that that's actually going to meet all of their requirements. With the FEA-led design or the CAE-led design, the customer has got much better confidence in your business development quotes because when you come up with a concept, you know how much it's going to weigh because you've done the CAE work and you've shown that in order for it to pass certain load cases, it needs to be a certain weight, and you know what size it's going to be and what machines it needs to be manufactured on and so on, because that's all been developed using CAE and using FEA upfront. Now, the other benefit is that there's less cost to the business when the quote is done at the supplier's expense. Now, this is something which is quite likely. More and more OEMs ask suppliers to quote for business, and the carrot, if you like, is that they will win that business and they will be able to produce parts for cars that go into production. But if they don't win that business, then that is that concept has been done at their expense. Now, if there's savings of up to 80% from these conceptual studies, then clearly that's a saving directly to the business if that's being done at their expense compared to passing that cost on to the OEM. Okay, so hopefully those first few slides, if we come out of that now, so we've gone up to slide 13 there. Beyond that, we start to talk about what optimization is, and we start to talk about the theory behind optimization, the different sorts of optimization, the pitfalls that you might come across when you're using optimization, and some mathematical demonstrations of optimization. We're going to look at those the second half of this, and all of those terms there from slide 14 onwards. We're going to look at that in the second video. So in this first video, what we've looked at is essentially this. We've looked at FEA in the product lifecycle. We've looked at conceptual design, conceptual example. We've looked at a comparison of costs and timings between a CAE-led and a CAD-led concept. And then finally, we've talked about going from concept through to production. So that's what you should get out of this video, an understanding of how CAE and how FEA and how optimization impacts on the product lifecycle. In the second video, we're going to move on and we're going to have a look at optimization in a bit more detail. So if you've got any questions on any of that, please let me know. You can either drop me an email or speak to me in class. Okay, so until next time, I'll see you then. Cheers, bye-bye.